Hello, my name is Richard Trett. I'm the Managing Director of AXT. I'm pleased to open this introduction to this webinar conducted by AXT in collaboration with our partner Sigray. AXT is a dynamic distributor of high-tech instrumentation in Australia and New Zealand. We have a large product range covering microscopy, microanalysis, nanofabrication and nanotechnology. We pride ourselves in building strong partnerships with our customers and suppliers, bringing together the best in scientific innovation and research with cutting-edge instrumentation and characterization. Truly unique tools to facilitate your research. This webinar is titled An Introduction to the Sigray Attomap and was presented by Dr. Wenbing Yun. Dr. Yun is a leading researcher in X-ray imaging, an innovator, a serial entrepreneur, an OSA fellow. He has over 60 issued patents in X-ray technology. From 2000 to 2013, he was the founder, CTO and president of X-Radio, a company specializing in high-resolution X-ray microscopy. Under his leadership, the company was established as a worldwide leader in high-performance X-ray microscopes and optics and grew profitably to 100 people in the Bay Area of San Francisco until it was acquired by Carl Zeiss. Post Zeiss acquisition, Dr. Yun started Sigray with a mission to make accessible an entire portfolio of Synchrotron-like analytical tools to laboratories. The products already include the Attomap MicroXRF, Zanes, and a nano CT system, and a range of optical components in the new X-ray source. Now I'll pass over to our webinar conducted by Dr. Yun.
Thank you for the introduction, and thank you everyone. For add a little bit more is that my background, I spent many years at Synchrotron, and my first company, X-Radio, was really commercialized what I have done at Synchrotron facility. So that one was reasonably successful and was acquired by Carl Zeiss. And my new company want to do the same thing, essentially trying to bring synchrotron capability to the lab. And in this presentation, I will go through, focus on one particular area, which is actually microanalysis, which is a topic of today's seminar, webinar. So, oh, shoot. So Sigray's mission really is to bring synchrotron capability to the lab. There are two key areas. One is that we can increase the actually source substantially. Another one is that increase make actually optics much better. So overall, we'll bring more photons, actually photons on the smaller spot to do microanalysis, get better sensitivity. So we have a lot of innovative concepts, and most of them, besides the MicroXRF system we are talking about today, we also develop other systems. For example, spectroscopy, and also with the exploration of X-ray microscope, NDA with Zeiss, we are building X-ray microscope also, but we are not going to talk about that today. So this slide gives what we are doing really. We're doing begin to do X-ray imaging, and we do composition mapping, and also we on the upper right cost, yeah, upper right screen, we are doing absorption spectroscopy also, but we are going to focus on the micro position mapping, which is MicroXRF. So this is a slide highlight what we can do, and this is a fly scan 5 millisecond per point, 4,000 by 2,000 pixels. So it's 8 megabyte of pixels of a rock sample, and it has multiple colors and representing 3 different elements: iron, potassium, and titanium. Actually, we collect many elements, just highlight what's the capability. This slide actually was not possible until recently with our system in the laboratory. This was done at 10 micron spot size, scan over large area, and get a lot of information. We will get detail later about this. For people who don't know about what is MicroXRF, is the basic principle are very simple. Essentially, each atom, each element has a nucleus in the center and also have electrons orbit the nucleus. So each of the electrons have a certain binding energy. And each element, as a consequence, because each element for each electrons have a signature. So based on the electron, information on the electrons, which one can get information about the element, which is a signature of an element or fingerprint of that element. Currently, there's quite a few techniques evolved doing composition analysis. There's atomic absorption spectroscopy, and on the very top, and in the center, there's actually based on electrons, that's actually fluorescence, and use actually excitation called XRF, and use electron beam excitation is the EDS, and sometimes also use proton called Pixie. And compared to all this technique, X-rays offer much superior sensitivity and flexibility. For one thing that, for example, X-ray don't require vacuum. And in the later, I will also talk about ICP mass. X-ray analysis also offers superior capability than ICP mass. General ICP mass is volume. Later ablation ICP mass is spatial resolving capability, but which is comparable to XRF, but has a severe limitation I will talk about later. So let's talk about the advantage of actually excitation over charged particles. Charged particle has electrons and protons. This slide has been available many years ago, prepared by Dr. Carly Spark, Oak Ridge National Lab, who is one of the pioneers for microanalysis. On the vertical axis is called actually fluorescence cross-section, and the bottom is atomic number. Essentially, based for the atomic number on the bottom, the larger number, the higher the number, the better on the vertical axis. So as you can see, actually excitation is far superior than electron and proton. So that's a basis why actually fluorescence analysis are widely used and have offer much better sensitivity than electron, for example. So the detail is explained in the number of the point, but the key point is actually is far superior for analysis. So give one of the major difference, actually excitation versus electron excitation is signal to background ratio is drastically better, as can be seen from the slide, and which is analysis of a material. As you can see, the signal to background ratio is really superior with actually analysis. So compared to many actually fluorescence-based technique, there's semi-EDS, electron. The first two are based on electron beam excitation, and the center one is based on the ICP mass with a laser ablation, and there's SEAMS. And relative sensitivity, as you can see, actually microanalysis is really good, and absolute sensitivity, if you look at that, is substantially better. Actually, I put picogram MicroXRF. Currently, we can do attogram or femtogram, which is the next slide. For example, compared to current system, we provide order magnitude better relative sensitivity and absolute sensitivity. And spatial resolution is 8 micron to 10 micron, which we routinely get. So actually, the excitation, traditionally, all MicroXRF use single actual energy or single target material, but use our actual source can provide multiple excitation energy which is very important, and we'll be explaining in the next few slides. For example, the first column, there's a many element of interest, assuming you have interest in that. The top, there's quite a few elements, target material, for example, aluminum target, rhodium target, copper target. They produce certain characteristic line for as excitation beam. So as you can see, in the table, the larger the number, the better, give you better signal. It's directly proportional to signal strength. As you can see, based on for given element, there's optimal actually excitation. For example, like I give example, sulfur. If you use a 3 keV excitation, you have a 7,700 unit of actual fluorescence cross section. But if you go to copper anode, you only have 550. And so clearly, rhodium L line will provide about more than order of magnitude better signal. And for example, like a copper, if you use like a zinc, if you use all the first 4 elements, the 4 actually excitation energy, first 4 column up to 9.2 keV, you cannot excite that, but it has to go to much higher energy, like 9.4, use a platinum target or use a moly target. So just want to use this slide, and it's very important for given element, select right actually target. Right now, we are actually source, the only source in the world. In one single actually source, you can select multiple target. And we will explain that how we do that later. But it's really important to, from this table, to know that ability to select actual energy is highly, highly important. So this is another example. For example, if widely used actually source use copper target, but if you want to analyze iron, trace element in steel, if you use a copper, all the iron atom in the sample will be excited and produce a huge background. Very hard to get the high sensitivity detection. But we can use iron as excitation actually source. In that case, all the iron atom in the sample will not produce actually fluorescence, so you have very low background. So with the target, not only you can increase the sensitivity in the previous slide, and by selecting material, target material, you can also suppress the background. So it's very important to have again, it's very important to have the capability to select target. So another important component, so we have 2 major important components we'll just describe over the next few slides. And typically for microanalysis, you have a source, you need optics to focus on small spot. So essentially, for this, in order to get a lot of actually flux on the focus to produce more signal, is that you want to have a source as bright as possible. You want optics to collect as large solid angle as possible from the source ability to focus on small spot. So over the next few slides, I will explain how we produce actually source with high brightness and with multiple target material in the same actually source. And also explain how we get why our optics is far superior. So regular actually source is that you bombard electron beam on a target, you produce X-rays. So the central part of the target get the temperature elevated because electron beam carry a lot of energy, so it began to melt. So improving the target thermal dissipation properties is very important to improve the enable large number of electron bombarding the target and produce more X-rays. So in order to do that, obviously you want to have a high thermal conductivity material, to be the target. And also you want to have a large thermal gradient. I just missed a question there. Someone sent a question there? I'm sorry, I might have missed a question. Probably I can answer that later. So our target is unique. We have a diamond substrate and put metal inside diamond. By doing that, we have a far more better thermal conductivity for the target. And also by microstructure the target, we have a larger thermal gradient for the target. So as a consequence, we have a much better thermal dissipation property. We can have more electron bombarding the target and produce more X-rays. So this is a slide just illustrated diamond's far superior material to use as part of the target. So when we do that, this slide illustrates how we get multiple target material on the same X-ray source. We microstructure the anode, and we have multiple different metals put inside the diamond. As a consequence, we produce orders of magnitude higher X-ray brightness, and we have multiple energies one can choose for excitation. You can easily switch from one target to another. And also we can get a very small spot that due to our electron optics design. So multiple target, for example, copper, moly, tungsten, silver, rhodium, and we can also do other elements, and mostly enabled by the microstructure, because, for example, like some of the metal has very low thermal conductivity, like tin, nickel. We can still embed into diamond and produce the characteristic lines we like to have. So the source is look like that. The diameter of the source is like Coke can. This source is most powerful X-ray source developed ever for a sealed X-ray tube. Just compare what is commercially available source with what we have. A microfocus source produced, commercially used, widely used, is 50 watts over 50 micron spot. So the most important is the watts per square micron. That's really related to how bright the X-ray source are. And there's a microfocus, then the liquid metal jet, as you can see, and there's our source. Clearly, if you can see that our source in that number is not as bright as a liquid metal, but as a liquid metal only has one target material. So as I have shown before, you can get orders of magnitude more fluorescent signal based on by selecting the proper X-ray energy. So we can have a 4 target material in the same X-ray source. You can easily switch. That's more than offset. Have a superior gain over the single target with liquid metal. So another advantage is our X-ray optics. Currently, all microfocus MicroXRF system use polycapillary optics. One of the major drawbacks is the focal spot is strongly depends on the X-ray energy. You know, the X-ray tube typically contain multiple X-ray energy, continuous X-ray energy. For example, if a higher energy focus on central part and lower energy like 8 keV focus larger spot, when you go to lower energy at like 4 keV, the spot size is much bigger. And compared to our X-ray source, all X-ray energy focus on to same spot. So we don't have for our X-ray optics, the focal spot is an independent size, independent of X-ray energy. So this picture illustrates some of the problem with the current X-ray source, polycapillary optics, and advantage of our source. For example, the left figure on the left essentially indicate for our focal spot remain 10 microns thereabout. And for all X-ray energy, polycapillary has a linear dependence, inverse linear dependence with X-ray energy. So another one advantage, probably particular for people with a geology sample, the surface is not smooth, irregular semiconductor devices. We have much larger working distance versus polycapillary. In order to get 10 micron spot, we have our focal length is 30 millimeter. For polycapillary, it's about 2 or 3 millimeter. So as you can see, if the surface changed by 1 millimeter, for us only changed by 3% focal spot, but for polycapillary, that changed by factor 2, 50% in terms of the focal spot size. So it's very important for polycapillary. You have polished surface, a flat surface, and for our system, the irregular sample surface is just fine. So we will describe some capability of our MicroXRF system. And system configuration is illustrated in this slide. We have microstructure X-ray source. We have our capillary double paraboloid capillary focusing optics. You focus on sample, you collect with a silicon drift detector. So we can have large number of X-rays on the small spot, and it has a fairly bright X-ray source and very good optics to collect and focus X-ray on the sample. So this is more schematic, have source, optics, and what you notice on behind the sample is that we have an X-ray camera that has about micron resolution. And if you want to have a transmission images, then you can also look at the get transmission image of the sample. Additionally, we have optical microscope, which enable us to co-register, look at the sample, and select region of interest to do fluorescence mapping analysis. So these are some specifications of the system. Spatial resolution down to 8 micron, and actually flux that's over 10 to the 8th, that's comparable to some second generation synchrotron beamlines. And we have a very high detection sensitivity down to femtogram sensitivity. And relative sensitivity can go to sub-ppm. And fly scan, we do constantly to do fly scan 5 milliseconds per point. And it's a very modular design and have a, as I said, optical microscope and transmission actually camera. And we can also upgrade later on to do MicroXRF, MicroRD. So this slide showing some of the scanning of the based on resolution, Siemens style resolution pattern. And this sample is a gold microstructure. As you can see that we can see resolution down to a few microns. Next slide will show that. And the curve on the right is a line scan across one of the line. And you can see the focal spot is about 8 microns or something. So we said give a few application examples, and can be used a wide range of application. Today probably we'll focus on geology, some plant and semiconductor application, but the application area is huge. So first of all, want to show you we do have some femtogram detection sensitivity in 100 seconds. And what it translates femtogram is that over 10 micron area, we have a subatomic layer sensitivity and down to 0.1, 0.2 micron atomic layer thickness. And it's equivalent to 100 nanometer nanoparticles. So if you have a nanoparticle in plant or in something you want to detect, that's a sensitivity we can get to. So this slide is that we put nickel, standard nickel film on top of silicon wafer. And from 5 angstrom to 100 to 10 to 15 angstrom, we have very good signal we have data analysis capability to do data fitting on the fly. And so we do this repeatedly, and within 100 seconds, we can get 1% repeatability. So that's, there's no laboratory system capable to do things like what we do. One of the applications is for semiconductor application here. And we mapped the gold thickness on top of this structure on the left, and we do data fitting, and the data analysis, the measurement was confirmed by electron microscope, and this was in collaboration with Professor Aaron Judge from Germany. Another one is for plant example showing the capability for plant. And as you can see, this is scanned over a huge area. And 10 millimeter, we scanned over about 70, 80 millimeter long, one direction, another one about 10 millimeter. This is, you can see root, and there are several elements shown here. There's from manganese, calcium, phosphor, sulfur, and cadmium. They're major interested to see cadmium uptake for this particular plant. So this one is done in fly scan and 10 milliseconds per point. The scan is over many megapixels. And this is a tricolor select area image, and I can see the resolution is superb and a very high, good sensitivity. These are another two examples. One is a root and plant leaf, and another one is leaf uptake of trying to get information on serrage in red color. And I think probably there's more interest on the geological sample in Australia. And this is another large area scan, fly scan 20 milliseconds per point, and multiple elements are shown here. And I will show some analysis later. And this one has a element for many different elements showing their mapping. And segmented images shown here is essentially each one has one color and with multiple elements superimposed, and you have this map. So this one has like 5 different elements, and the superimposed generate this map. And we select one particular grain in this image, pyrite grain, and to do a higher resolution, longer time map. And these are over a single pyrite grain. Obviously, you can see that within a pyrite grain, there is a different distribution. For example, like potassium might have a distribution, a uniform distribution, and also tin has a uniform distribution. Otherwise, other elements are reasonably uniform. Iron has some, as you can see, that there's low concentration in some area of iron that's correlated with potassium and tin. So we can do this one. The data analysis well established. We can do peak fitting and background subtraction. We have fundamental parameter analysis capability to do that. So I want to show our system compared to one of the leading competitor. Probably don't see the name, but you might know. We are not allowed to see exactly the name. And this is the same sample one of the customers sent to us. And this is the same area. And left is our image, and right is from the competitor. And you can see the structure, the fine feature, and clearly see the resolution and the sensitivity and the superiority of our system. And for example, this is select area and the 2 arrows, and you can see the resolution. And within the pixel, we can see much more information there. And there are some small spot areas that they just missed. So one last thing I want to talk about is that MicroXRF do have advantage over LASCP mass. For people who don't know, LASCP mass is laser ablation to remove material and feed into ICP mass spectrometer. This one can be used to do solid. And for example, in this periodic table, many elements actually ICP mass would have trouble, as illustrated in the next slide. For transition metals, ICP mass are not particularly good because there's a polyatomic interference. So the sensitivity, relative sensitivity and absolute sensitivity are not as good as a MicroXRF. And for some other element like carbon, nitrogen, oxygen, fluorine, and those chlorine, ICP mass has a very low cross-section and sensitivity are pretty low. MicroXRF are far better for those elements also. So with that, and again, pull up the capability of the system, I think I will leave time for questions and to answer questions. Thank you very much.
So is there any question? If there is, yeah, you could, as I mentioned earlier, you could write it actually in the chat box. I think there is one that just popped up.
Phil. I think Phil has a question.
Yeah, hi, can you hear me?
Yes. Can you speak louder, a little bit louder?
Yeah, sure. Yeah, the last couple of images you showed, I was just wondering what the diameter of those 2 samples was.
Do you mean those?
The one just before, that's it, that one.
You mean this one?
No, the one after that.
This one?
Yes, that's right.
Yeah. I think this was the 3 centimeter or 4 centimeter diameter sample.
Okay. And can you, you know, zoom in on those images?
Yeah, we have a zoom in. For example, next slide actually is one very small area zoom in. Just select the area just to see the difference.
Okay. And what's the scale on this one?
This scale, the circle is, let me see, the blue arrow indicate we have several pixels. So that's the one of the arrow not point to the blue arrow, not point to the circle. That one is like 20 micron in the vertical direction, probably 30 micron in the horizontal direction.
Okay. And sorry, one other question while I'm on. With the unit that you showed, what's the maximum area you can scan?
Currently, we can scan 100 millimeter by 100 millimeter scanning area.
Is that just a limitation of the stage you have, or?
Yes, currently the stage, we can make it bigger if that's important.
And how long does it take to scan that size area?
The scan that 100 millimeter by 100 millimeter, we can finish. We have the flash scan. Actually, for that we were use a larger spot. We can finish like 20 or 30 minutes.
Okay.
Sometimes we call fast survey scan. We can rapidly scan, then select the area to do high resolution scan.
Right. Okay. Thank you very much.
Yeah. The program is set up so that if you select area can queue, and many area of interest as a queue will automatically scan multiple areas without interruption.
Oh, okay. You can program it.
Yes.
Right. Yeah, my interest is in refractory materials, which are obviously made from, predominantly geological minerals, but also have some synthetic components in there. And also ceramic materials, engineering ceramics, looking at larger areas of those. So I'm very excited with your equipment. So thank you for your demonstration.
Yes, if you have a sample, I think it's a very convincing story is that to convince you is that to do a demo for your sample.
Okay, thank you. I'll contact AXT.
Yes.
Thanks very much.
You're welcome. Yeah.
There are more questions, Wenbing, from Anthony and James.
It's a.
Read out that question.
Hi, Wenping. We just had a quick question. You mentioned on one of the slides that the system can be upgraded to MicroXRD, and we were wondering what the benefits of using that upgrade would be compared to traditional XRD.
Okay, I think a lot of the traditional MicroXRF give you composition information, and if you have MicroXRD, you can together can uniquely determine the mineralogy, and there are minerals may not have a similar chemical composition, and may not have give you the same crystallographic. By adding crystallographic information, you can uniquely determine what crystal lattice and all that.
Yeah, sure. So how would this system perform compared to what's already out there on the market in terms of MicroXRD and traditional XRD systems?
In terms of sports side, in terms of flux and speed, and I think we'll mainly, for example, in terms of a if you need a high resolution, higher sensitivity, we definitely will offer far better in that regard. Similar to the horizons, for example, like a slide we are just saying. Right now, we can focus on particular particle and to do with a smaller spot. And one of the things which is very critical for micro diffraction is that all actually should focus on same spot. Right now, for example, if you use a polycapillary, everyone else use polycapillary, the different energy focus on different spot. So you might get different part of the sample, different grain to contribute diffraction peak.
And just following about this question, if you upgrade it for MicroXRD, are we still able to choose the 4 sources for MicroXRD?
Yes. MicroXRD we will implement in 2 fashion. Obviously, either if the sample is thick, we have to get like a tilt the sample to get diffraction so that I actually don't have to go through the thick sample. If you have a thin rock sample or thin sample actually can transmit through, then you can have a fluorescent collect from the top and get diffraction from the collect diffraction signal from the back.
Yeah, so the MicroXRD is mainly using for transmission mode or reflection mode as well?
Please say that again.
The MicroXRD is the sample for X-ray diffraction. Is that going to be a transmission mode diffraction or reflection?
We can have we are planning to do both. Obviously, if the sample very big, might be problematic. And sample when it's small, we can do either reflection on the ones, but if very thick and big sample, probably even the reflection will be having problem.
Is there currently a commercially available system doing the reflection mode only? Or
I don't know other people have that or not. A micro diffraction alone, yes, there are a system can do micro diffraction alone. The spot size usually probably currently is 100 micron or something, because polycapillary is really not good for micro diffraction, because different X-ray energy focus at different spot, and it's very hard to quantify.
That's actually something I'm thinking that's a big advantage using your optics compared to the traditional optics for MicroXRD. And another thing I want to ask, if this upgrade to MicroXRD, what's the detector you're going to use?
Yeah, right now we are evaluating several. We even consider to have the one of the photon counting detector. Really depends on the pixel size. That price can go up for like a 2 megabyte pixel can go up to $1 million. So we have to figure out what is just detector alone. Mostly Synchrotron use them. So I think there's a range of detector we can choose, and depend on the budget and what we can offer also.
Yeah, I understand. The good detector are very expensive. So you in the process of developing the new technique on upgrading it to MicroXRD, right? It's not actually commercially available yet.
Oh, the MicroXRF right now we are using commercially available silicon drift detector. That's XRD. We have several choices, and from lower cost to high cost choices, and we are still evaluating what to choose, which one to choose, and we are trying to figure out what is the market would be accept. And we could have a very high-end detector, but it might be too expensive to be adopted in the early stage.
Just curious, is there a model machine set up already, or it's still?
Not yet. That's we are still in the planning stage. The MicroXRD. We have some design concept, but we have not. That is not available. The MicroXRF, we have multiple systems in-house to do demo.
Okay, thank you very much.
Thank you.
So this makes actually a great opportunity for early adopters. If you like to contribute and collaborate on projects like that, we can actually kind of negotiate and talk about that later on.
Yeah, that's very good. Yes.
So Wenming, Anthony actually has got some questions, but he doesn't have microphone, so please read them from the chat box. And
where do I read?
I have to read it for you because I think he wrote. Yeah, sure.
Yeah.
So one of the, let me just go through the questions from top. For XRF mapping at 5 microseconds per pixel, what would be typical detection limits for trace elements?
5 milliseconds, you mean?
Yeah.
5 milliseconds, I think we can do probably 100 part per million on that level. Depends also what trace element, and is that if X-ray energy around like between 5 to 10 keV or 12 keV, that is the energy range. If, for example, a very high Z element or something, very low Z element, that is problematic. Also, the sensitivity will be loose. So usually, what we Anthony probably answered. Usually, often, our experience is that, for example, we have imaging invisible gold. Usually, they are associated with arsenic or sulfur. So those are signal usually very strong. So we can select masking this area, essentially a binary mask, and to find those grains with those elements, and we can do longer per point. Did I answer your question?
So okay, great. Yeah, you have. Another question is that what is the lightest element you can analyze?
Right now, we can we do two. One thing is that currently we can do like a magnesium with currently with that's operating in helium, mostly helium path. We are building another one which is that only going to accommodate 4-inch the sample that we will go to as low as carbon. And that's a module can be attached to the system. One can remove that, but that is in vacuum operation, so that we have a separate detector, and that go down to carbon.
And another question is
carbon, beryllium, more boron. Those.
Okay. For quantitative analysis, how does it cope with the matrix corrections to account for different X-ray penetration of different energies of incident beam and generated X-rays? Are standards required?
We usually to do two things. One thing is that if a known sample, we have a fundamental parameter. We use a major element as to know what is the material matrix. And to do that, the absolute accuracy probably going to be about a few percent, not going to be better than 1% typical. But if you have a reference standard, we can do very good. Below 1% is reasonably easy. For example, we detect a subatomic layers thickness on top of silicon. In that case, we can do 0.1% sensitivity in 100 seconds. So one can scale based on that. In that case, we do know the substrate material, so use that we can use a fundamental parameter to determine the thickness.
So did that answer your questions, Anthony? Is there any more? Okay, perfect. So great. So as Wenbing offered, if you had any sample that you wanted to have a look, please let us know. We can actually arrange a demonstration on your samples. And please keep your eyes on our next webinars. Hopefully next webinar with Sigray group will be on X-ray absorption spectroscopy. We haven't yet decided on the date, but soon we will, and we'll send you an invitation, and if you are interested, we'll catch up then. So I guess that's it for today, and thank you very much, Wenbing. It was a great presentation. I'm sure everyone enjoyed, and I leave you guys and have a good day. Goodbye.
Thank you very much. Yes, thank you for organizing the meeting.